Now let's look at how do we basically understand the cyclicity present in a time series data, right? The moment we understand the trend, how do we identify the trend? How do we identify the seasonality? The one more important aspect that needs to be understood is the cyclicity that is present in the data, right? So just trying to understand whenever we are talking of cycles, if I'm talking about rigid cycles, it is more like an up and down movement like this at different points in time, where the pattern is more rigid, more solid, more clearly visible. This is one dimension of cyclicity. And in some cases, the pattern may not be rigid and is not that clearly visible at all. Right, majority of the real world business, economics, financial data, I find them they are not much of rigid. So so a clear cut definition that comes out for cyclicity is any kind of dynamics that is present in the data which is not captured by either the trend or seasonality. If there has been a trend, it is captured by the trend analysis. If there has been a seasonality, it is captured as a part of the seasonality adjustments using the seasonal dummies, etc. Anything that is not captured by trend and seasonalities, it is going into the cyclicality analysis. So as we move and move in terms of understanding the cyclicality mechanisms, we can very simply understand that portion of the variation in the data that is not captured by trend and seasonalities. We are looking at cyclical analysis on them. So from that perspective, almost every data, every time series data will contain the cyclicality in some form or the other, and there are so many patterns. We'll be looking at them in the next few sessions. There are quite a good number of patterns that are more and more associated with cyclicality. It's not that easy to identify the cyclicality like we have identified trend and seasonality. Trend and seasonalities are more relatively more easier to identify compared to identifying the cyclicity in the data, right? So to identify that particular stationarity in the data, to identify that particular cyclicality in the data, first of all, we need to understand the concept of covariance stationary data, right? Generally, whenever I talk about a time series, right, we are capturing the values at different points in time, y1, y2, y3, so on, yn. For the last n periods, it could be n months, n years, n quarters, n days. So y1 is the data at the first point, second point, and the nth data. So this is the typical time series data, and we are calling it as a realization. Different values that your variable can take at different points in time, and a sample of that, which is a finite. This could be an infinite data set as well, right? For every second I can expect a different value being taken by y. If I'm assuming that the y is a stock price data for a particular stock, for every minute the stock price is going to change. And when I'm talking about the realization of the values for that time series, it is as good as the data right from the beginning of the stock. For every minute change, whatever is the change in the stock price that has come out, that forms the realization, which is almost an infinite set. Now if I am taking at some pre-specified points in time, one day, at the end of first day, at the end of second day, at the end of third day, it means I am taking a sample subset of that entire realization, and I call that as the sample path. The intention in understanding this is identify the probability structure of that past data. if the probability structure is changing quite drastically, then obviously I cannot do anything, because the past is nowhere a reflection for the future. The future is nowhere dependent on the past data. Everything is random and I cannot use it for my forecasting purpose. So from that standpoint, we are trying to understand the process, whether it is covariant stationary. If at all some process is covariant stationary, then I can very well make a couple of steps forward in terms of doing the forecasting of the data using the concept of covariant stationarity. And what it simply means is, any data that I look at, if the mean and the covariance for different combinations of the values, if they are the same across different time periods, if they are the same, if they are identifiable, if they are constant, then that is what will ensure the covariant stationarity to the data. Now, just to get that covariant stationarity, I'll try to generate one simple random data set. Right, I'll generate a normally standard normal inverse data set using a random function. Let's try to understand whether this particular data set is covariance stationary or not. I'm generating a values of around 500 observations. Okay, let's assume that these are the real-time values that we have got for some particular process. Let me not get more. So this is like a simple data that we have collected. Now, what I would like to do is, I will try to find out the mean. Right, I would like to find out the mean at different points in time. So let's say the mean of 100. So if I try finding out the mean from what, or probably I'll take the mean of 50 at a time. So I'll try to find out the mean of the first 50. Right, I'll try to find out the mean of the first 50 elements. I've got that the mean is around minus 0.06. Similarly, when I am taking the mean from, let's say, 51 to 100 elements, right, when I am taking the mean from 51 to 100 elements, okay, let me try out the mean of 51 to 100. Okay, this is the mean of the values from 51 to 100. Even this is 0.27. Probably I'll take a mean of 11 to 60. Right, I'll take the mean of 11 to 60. Okay, this is around minus 0.08. Now what we could see is the means. If I am taking mean of 151 to 200, right, when I have taken the mean from 151st observation to the 200th observation also, the mean is not too different. So across different points in time, the mean is more or less the same. Right, if the mean is more or less the same, or probably let me try out the mean of 451 to 500 values, right, just to see across different points in time. It's not constantly increasing, it's not constantly decreasing. For a data which is completely trend based, probably it cannot be covariant stationary, because this is more and more random in nature. I'm seeing that yes, the mean of from 451 to 500 is also 0.15, 151 to 200 is also 0.13. More or less they are the same. There is no pattern of increasing or decreasing that is coming up. So that means mean of the current and the past values is more or less the same. Similarly, let me take the covariances. I'll take the covariances, let's say from 1 to 50 and 51 to 100, which means a lag of 50. I'm taking it for a lag of 50. Let me find out the covariances. Covariance taking the 1 to 50 as one set and 51 to 100 I'm taking as another set. It's a lag of 50 which I have taken. The covariance is showing as minus 0.19. Now the same 50 lag, I want to take it as covariance between, let's say, 11 to 60 and 11 to 60 and 51 to 100, because it's again a lag. Okay, here I'm not taking, here I'll take it as 61 to 110, because again a lag of 50 only is what I'm taking. So I'll take the covariance from 11 to 60 on one side, and I'll also take it as 61 to 110, which is giving me a lag of 50 again. So again minus 0.20. Otherwise take it as covariance of 201 to 250 comma 251 to 300. I want to just look at. So the covariances I want to look at from 201st observation to 250th observation, comma 251st observation to the 300th observation. What I could see again, it's much smaller kind of value. Now what we are simply saying is, as long as the mean and the covariance, now probably I want to change a little bit. I want to find out the covariance again between, let's say, 1 to 20 and 21 to 40. And I want to find covariance between 1 to 20 and 21 to 40. This covariance might be slightly different, right? Because it's for a lag of 20 only. Covariance between 41 to 60 and 61 to 80. This is for a lag of 20. Right? Covariance between 41 to 60, comma 61 to 80. What I could see is, see, what we are typically saying is the mean and the covariance should be more or less related, should be more or less constant. And what we say is the autocovariance with a lag S is dependent purely on S, and it should not dependent on the current time period. Means the autocovariance should not show some kind of increasing trend or decreasing trend. More or less, if it is slightly up, it should come back to the, it should come back to that constant. If it is down, it should again go back to the constant. So whenever we are seeing some particular series of data where the mean and the covariance are more or less uniform across, that is what we call as covariance stationary data. And understanding of this covariance stationary is very much important because it provides the summary of the cyclical dynamics, because majority of the times we find the data that come as the errors in the regression process, we find that they are majorly they are after the trend and the seasonal forecast, whatever the numbers that are left, whatever the errors that are left, we find that they follow this kind of covariance stationarity. So we can very comfortably get into the understanding of the cyclicality dynamics in that covariance stationary series. right? And in reality, many business applications, by direct visualization, they may not be covariance stationary. If I'm looking at the prices across, probably they may not be covariance stationary because they show some kind of trend in them, they show some kind of seasonality in them. So prices as such may not exhibit the covariance stationarity behavior, but whatever are the cyclical component that are left after modeling the trend and seasonality, whatever the error that I consider after modeling the trend and the seasonality, that portion can very well be covariance stationary, which means I can use the principle of covariance stationarity to try to model the error that gets generated in the process, because many a time that error may not be independent. You will find, if you find that the residuals, which are the errors, they are not serially related, then they are completely independent. But they see their correlation may be zero, but they may very well be having some kind of they may be more or less, may not be independent of each other. So that's the reason by understanding the component that are left after forecasting the trend and the seasonality, we can very well get into the understanding of the cyclical component. And in the other side, probably the prices may not be covariance stationary. But if I do some kind of a small transformation on them, and let's say convert them into growth rates year over year or period over period, they may be more and more covariance stationary. The prices as such may be showing some kind of a trend, but if I convert that prices into growth rates or change in prices, I could very well see that that could very well express a covariance stationarity as the principle. So understanding the fundamental of covariance stationarity will help us in trying to model the leftover portion after modeling the trend and the seasonality component. Then, apart from covariance, I could even look at correlation, because correlation is a much better measure compared to covariance. The reason being, covariance, there are no boundaries. It could be a very heavy negative value, it could be a very heavy positive value. It can take values literally between minus infinite to plus infinite. So I cannot say whether the relationship is strong or weak just by observing the value of correlation covariance. Even a covariance of 10 million may not be a significant may not be a significant relationship between the variables, whereas for some other data set, even a covariance of 10 could be a very significant covariance. So directly looking at the covariance, I cannot typically say whether it is very high or very low. Is it significantly higher or lower? So there is a kind of standardization of the covariance, normalization of the covariance that is generally performed, and that is what we are calling as correlation. So what we typically do is, whatever the covariance that we have got, we do the standard deviation between, we divide it by the standard deviation of the two values to typically arrive at the correlation. Now let's see, in this case, the correlation, let's say between 1 to 50, the correlation between 1 to 50 and 51 to 100. Right, the correlation is around minus 0.16, whereas in this case, if I am taking it between 11 to 60 and 61, 11 to 60 and 61 to 110, This is coming out to minus 0.17. You see the difference is slightly narrower. And even here from 201 to 250, if I'm trying out the correlation between 201 and 250, 201 to 250, comma 251 to 300. I try to find out the correlation. It is giving me 0.03. Now what I can very clearly see is the covariance. Similarly, when I look at correlation between, let's say, 1 to 20, comma 21 to 40, correlation is minus 0.7, and I look at it again between 41 to 60 and 61 to 80. Correlation is working out to minus 0.16. Now, correlation is a much better measure compared to covariance because it lies between minus 1 to plus 1 and it is unitless. And it talks about the strength of association that is underlying between the two variables. So what we are very much interested in is the autocorrelation function, which we, for our data, we are more and more interested in finding out the autocorrelation function with different time lags. Okay, so for this particular data, I will try finding out the autocorrelation with a time lag 1. Right, let me take now the data sets. We'll look at time lag 1, 2, 3 up to 100, up to some numbers. Right, let's say we require, okay, this is current. Then I say time lag 1. So for time lag 1, I'll have this value as this and it proceeds. Then I take time lag 2. From here I start this value as this and I proceed. Then time lag 3 will take it as this and we are proceeding. Time lag 4, again we'll consider this to be the value, will proceed. Time lag 5 also goes the same way. Like this, you could very well see different kinds of time lags. Probably let's do it up to 10 or 15 because we have to understand a few more patterns based on that. Okay, I'll take the time lag 7. Then I'm doing a time lag 8. The same process across. This goes as the time lag 9. All right. Let me do up to here. At least let's look at up to 12, or probably it's better that I do it up to some 15 or something. 15 or 16, let me do it to explain the concept much better. Now that we have 500 data points, we do not need to worry too much. Okay. Okay, I have taken 16 different time lags, and just to bring uniformity in all of them, I am deleting all these records, or probably let me take them from here to here. Let me copy and paste them as values directly so that I can delete each of them because they are not having too much of impact. Okay, so these are the numbers that we had with us, the different time lags for different points in time. So what I can think of is computing. I have around 485 records altogether because I had to remove a few of them. Now what I can look at is computing the correlations for each of them. The current, I'll try to find out the correlation with time lag 1, time lag 2. So here let's say I am looking at autocorrelation function for different time lags. So I'm looking at it as correlation between the current and the time lag 1. Coming out that the correlation is minus 0.01, and probably if I'm going up to 16, these are the kind of correlations that are getting generated. We have 16 time lags, and these are the correlations that got generated, autocorrelation that got generated. And what I would really want to see is a kind of a graph, or probably I want to test out whether they are statistically significant or not. Should I take them as an existing number, or can they be treated as zeros itself? So for that we know that the statistical test, I can perform a t-test, r into square root of n minus 2 divided by square root of 1 minus r squared. So r into square root of 485 divided by square root of, n minus 2 becomes 483 divided by 1 minus r squared. So this comes out to be the t value, and for this particular t value, and in none of these cases I see that the t value is greater. Probably let me just quickly work out on t critical value for 483 degrees of freedom. So I can take, or probably I'll take the t critical for, let's say, 5 degrees of for 485 degrees of freedom and a 5% level of confidence. If I look at for 483 degrees of freedom, I get that it should lie between minus 1.96 to plus 1.96, and I don't see whether it is significant or whether any of them are really statistically significant or not. If the absolute value of this is greater than the absolute value of this, I say in significance I'll say yes, otherwise I'll say no. So going with this, yes, this part is insignificant, this part is insignificant, only one of them is looking like slightly significant, that too at 5% level of significance. But if I'm going with 1% level, probably even that is really not looking anywhere significant, right? So which means the autocorrelation function absolute of this r into square root of n minus 2 divided by of 1 minus r squared. So none of them is evolving as significant in any of the case, right? None of them is evolving significant in any of the case, which means I see that the autocorrelation is almost closer to zero in each of these cases. So we can actually compute the autocorrelation instead of autocovariance and plot the autocorrelation. So in this case, these are the numbers that are working out as autocorrelations. And on the other side, one more important thing that we generally look at is on this data, I try computing the partial autocorrelation function, wherein we are trying to regress yt on the different lagged variables. This is what we call as auto regression. I am trying to do the regression. I am trying to find the regression taking this, the current value as the dependent variable and all these lagged values as the independent variable. So what is coming out if I am doing the regression like this? I could clearly see that I will consider this as the dependent variable. I will consider all these different lags. I will consider all these different lags as the independent variables with labels and try to do the plotting. Yes. So this is what is coming out. Intercept. This is the time lag 1, time lag 2. And I will see. So I'm doing an auto regression considering the current yt as the dependent variable and yt minus 1, yt minus 2, so on as the independent variables, and I'm trying to compute the expression. So it's as good as saying zero point 0, the current value yt is same as 0.02 times 0.02 plus 0.0009 times the time lag 1 value plus 0.024 times time lag 2 value and so on. But what I could clearly see is the p-values associated with almost all of them are greater than 0.05 except for this one. So I may say that probably TL9 there is some kind of correlation that is existing, very minute because the value is minus 0.09, but a very, it's not that ignorable kind, right? If I'm looking at it as a 95% confidence levels, I could see that TL9 is contributing, but all others are more or less not. Which means I could have clearly taken these as my partial autocorrelation values. So let me just take them here. Let me just take them here and paste them in the transpose form, wherein I'll get partial autocorrelation function, which is more or less similar to that of the autocorrelation. Okay, let me not take the constant TL1 to TL16. These are the numbers that came out. Okay, even I should be having one here as well. Okay, even here, if I look at these numbers, there is a small adjustment. This is a negative here, this is a small positive. Here, both of them are more or less the same. Now, I can try doing a kind of a plotting for the auto correlation function as well as the partial autocorrelation function. I can have both the graphs being plotted, and what I could see is they are fluctuating around 0, right? For as see for different time lags, I could see that the autocorrelation as well as the partial autocorrelation function, if I'm taking a lag of 1, there is some autocorrelation, taking a lag of 2, there. So more or less they are fluctuating around 0 itself. It's not that significantly different from 0 at any point, and they are more or less, they will more or less, initially they are showing much higher difference, but probably if I try out for another 30, 40 kind of lags, they should come even more waning down towards 0. So that is what one more important function that we understand. As the lag increases, if I see that the ACF and PACF, both of them are going closer to 0, then we say that that particular series is covariant stationary. Either I can see that they are completely, ACF is, let's say, gradually dampening to 0 on one side, or I could see that the ACF is okay, higher this side, but as we move, there is a gradual dampening out to 0 that is happening. That is a damped oscillation, and probably for some period the ACF is existing significant, and suddenly after this it is going up. Even those kind of things are possible, but as the lag is increasing, I need to see that the overall ACF and PACF should go much closer to 0. That is one more important characteristic in case of, as the lag is increasing, I want my autocorrelations to come closer and closer to 0. Similarly, the partial autocorrelations also should come more closer to 0. That is what is the understanding of the covariant stationarity present in the data. Right? Next, let's try to look at one of those important forms of a covariant stationary series, which is the white noise. And it's one of the important time series processes for forecasting, because it is something that we'll understand slightly later, that it becomes a major building block to construct the other core properties of the time series. At a later point, when we are looking at moving average processes or auto regression processes or ARMA processes, we try to use this concept of white noise, which will form the core. So that's the reason we have to understand the white noise. And whenever I'm talking about the white noise, we are more targeting about the serially uncorrelated kind of variable, which we have already tested with our data. The correlation across the different time points is more or less zeros. That is what is an understanding of the serially uncorrelated. In some data series, that serial uncorrelation may not be there, but wherever we see serially uncorrelated, which means when I am taking the ACF and PACF, when I am considering the ACF and PACF, as the lag is increasing, the value should go more and more closer to 0. So anything which is a zero mean, which was the case, the constant variance at any point in time, the variance should not be that different, and the serial correlation not present, we call that as a white noise. And if it is serially independent also, if I see that it is normally distributed, probably I should see whether, how do I test whether something is normally distributed or not? I can very well take I can very well take the skewness of that data set, the skewness of the data set with some time lag, yes, closer to zero. Even the kurtosis, if I take, I see that it is also slightly closer to zero, which means this particular data set is more or less normally distributed. Then we call it as a Gaussian white noise or a normal white noise. But in some cases, it need not be normally distributed, which means it need not be independent. If it is independent, we can even call it as IID, with which is a normally distributed white noise with a mean 0 and a variance equal to sigma squared, which is constant, right? And if we see any regression model, whatever is the errors that are left, let me open the earlier regression model which we have done for serial no, for seasonality forecast. Let's say if this is the serially forecasted kind of a data, I mean seasonality forecasted kind of a data. This was the predicted value. So let me simply take only the error rather than the error squared here, where I'll look at the predicted value minus the actual, or the other way around, whatever it is. So this is the, these are the errors that came out from after doing the trend as well as the seasonality forecast. Now let me try finding out whether these qualities are present in this. See, when I'm talking about auto disturbance in any regression model, this is the disturbance or the error in the regression model. I want to know whether it is white noise or not. If I want to know whether it is white noise or not, I have to find out the mean. Okay, I'll find out the mean of this entire process. Yes. Okay, the mean of this entire process. Okay, these numbers are not required. So this is where I have to check out the mean of this entire process is very much close to zero. And I should try out the covariances at different points in time. Right, for different lags, I should see the covariances. Let's say the covariance I would try out with a lag of 1. Okay, I'll see this one, covariance between this. Or probably I'll look at the correlation rather than the covariance. I'll take it between this and 1 period lag, resulting in a correlation of 0.92. And this time if I look at it with a 2 period lag, right, let me try the correlation with the 2 period lag. I'm getting it 0.85. This time when I try it with a 3 period lag, it's 0.77. This is how the autocorrelation is falling. Right, after a certain point probably it may go out altogether. Okay, with a 4 period lag, let me look at it. This is the 4 period lag. The correlation coming down and down, 0.67. And again when I look at it with a 5 period lag, so probably I can operate it out for each of the lags, different amounts of correlation. Okay, that's one. Then at the same time, so probably if I do it for a few more periods, it can wane off to zero. So it could be an indication that it is covariance stationary, because we have initially discussed that The ACF and PACF gradually go to zero as the lag is increasing. That is what is the meaning of covariance stationarity. And I am clearly seeing that as the lag is increasing, the covariance, the correlation is going closer and closer to zero. Initially it was much higher, but it started falling off. So came to the extent of 0.45, slowly falling down and falling down to the zeros. So that is a clear indicator that the covariance, so this is more or less covariance stationary. So anything that is covariance stationary and zero mean no serial correlation existing, that is what we call as white noise. But this may or may not be white noise in this case, because this is not white noise because there is some amount of serial correlation that is significantly observed. But in some kind of serially uncorrelated regular regression kind of examples, we see even serial uncorrelation being present. Not covariance stationarity is present here, but obviously it's not serially uncorrelated because I am seeing some levels of correlation that they are being present. And autocovariance and correlations for lags beyond zero. Immediately for a lag beyond zero, it should be zero. But in this case, it was not the case. But the example which I have taken here, I am seeing that beyond zero, the correlations are very much close to zeros. So this is more of a white noise, but the other example need not be a white noise for us. Now, forecasting an independent white noise is a very difficult thing because nothing is dependent on the past, so I can't use anything. But a dependent white noise, like this kind of an example, wherein I see some amount of autocorrelation in the error. I'm seeing some good amount of serial correlations in the error. They can very well be forecasted by understanding the cyclicality based forecasting principles. But if I transform the white noise, it can do some kind of transformations on the white noise. They produce results which are for the processes with much richer dynamics. And any one step forecast errors, typically any one step ahead forecast, I call the white noise is a forecasting error. If it is not white noise, it means that there is some amount of serial correlation. Some amount of serial correlation will lead to the forecastability of that particular variable, which means our forecasts are not better. So in any good model, any kind of deviation that came out between the actuals and the predicted, that portion should be white noise itself. That's one more dimension where white noise becomes more and more helpful for us in understanding. And in the white noise, we actually end up computing not just the unconditional mean and unconditional variances, we also look at the conditional mean and variance. We'll try to look at them slightly later. So it need not be a constant. When we looked at unconditional mean, unconditional variance, for the entire period, we are getting similar kinds of mean and the variance. But when I go with conditional, in some cases it may be a different altogether. And wherever I am seeing that the conditional mean is higher than the unconditional or lower than the unconditional, then it's as good as it is giving me an additional information in terms of doing the prediction. But for a white noise, even that scope does not exist, which means in a white noise, if something is a white noise, it can very well be visualized that it is more or less purely random and it can't help me in terms of doing any kind of predictions to any extent. And when we are talking about the forecasting the time series, we should be very comfortable with the operators, lag operators. Generally, we use the value letter L to indicate the lag. So when I say LYT, it means it is YT minus 1. L squared YT, I call it as YT minus 2. So like this, the different notations go up. Or similarly, when I say delta yt, it means yt minus of yt minus 1. The difference between the two lagged operators. Right. In general, we even talk about b of l, which is a polynomial of the mth degree, which is given with b naught plus b1 l. L is nothing but yt minus 1. So it's as good as b naught yt plus b1 yt minus 1 plus b2 times yt minus 2 plus bm times yt minus m. This becomes a very important expression in the time series cyclicality forecast. So we have to be very comfortable with the two lag operators, the L and the delta, because if I have to read if I have to read through any kind of article or a journal that is purely based on time series, these terminologies should be more and more understandable to me. So the distributed lag of the current and the past values also can be created with different weights. So B naught could be different, B1 could be different, B2 could be different. And if this need not go only up to M, it can go even to the extent of infinite. And this is what becomes the key for a lot of time series models and forecasts, which we would be seeing at a later point, coming out with the Garsh model, Arch model, Arima models, lots and lots of models that are used in the forecasting. They become the key, they become quite essential using the lag operators. Now, one of the essential theorems that come into the world of forecasting is the Wold's theorem. It talks about how do I fit a covariant stationary residual model. What is that additional information that I can gather, or what is the way I should proceed in terms of fitting a covariant stationary model? Because once I see that the data is covariant stationary, it doesn't mean that I can fit model. There are hundreds of time series models which are applicable to the covariant stationary data. So that is where the Wold's theorem simply says any covariant stationary process, if something is covariant stationary, you express the yt's as the summation of bi times the error. So express it in this particular form. Every yt, you express it right from t equal to I equal to 0 to infinite. I equal to 0 to infinite, you express this, which means if I want y2, it is as good as saying b naught times error 2 plus b1 times error 1 plus b2 times error 0. Similarly, if I go for y1, it becomes b1 times epsilon 1 plus b0. Sorry, plus b0 times b0 times epsilon 1 plus b1 times epsilon 0. And y0, the beginning y0, I will be taking it as same as epsilon 0. b0 times epsilon 0. Now, what it typically goes with this mechanism simply says is take b0 equal to 1 always. So you are getting the value of y0 same as epsilon 0. So you have the value of epsilon 0. Now you start finding out the values of b1, b2, so on. You do it as an iterative process and try to find out the values of b1, b2, b3, so on. So that is, and if I am trying to find out the sigma of all the bi squares, it should be converging to something, which means this should be less than infinite. This is what is a Wold's theorem saying, which means every process which is covariant stationary, you express it as a linear function of various errors, different time period errors, which are typically being called as innovations. You take them as a function of different innovation, because we are talking, whenever we are talking of innovation, it is nothing but one step ahead forecast error, and it has to be uncorrelated but need not be independent. So which means the conditional mean could be differing. Unconditional mean may not change, but the conditional mean could differ depending on the amount of information that is available until the previous period. Sometimes we may say, okay, during this entire period, the mean growth is, the average growth is 10%. But in some cases, okay, under the assumption that the last year it has grown by 20%, this year the growth may be 15%. Overall, over a 10-year period, the average is 10%. But given in the last 9 years, the growth is 20%, probably in the last year, the growth is 20%. I may have a different number for the 10th year altogether. That is what we are calling as a conditional mean. So, when we look at this ARMA models at a later point in time, we would very clearly appreciate the importance of the Wold's theorem, the kind of iterations that come out in terms of doing the forecasts and the estimate, which can really help us in a large greater way in terms of doing the forecasting for the cyclical processes. Now, when I typically look at from the sample, if I have to go ahead, which we have done for the example, the sample mean, I take the mean of the data. Probably let me take this example. I have computed the sample mean here just by taking the mean of these numbers, right? In case I have to depend on the samples altogether, I'm computing the sample mean through this, which is very close to 0. Then I'm computing the sample autocorrelations, which I have shown earlier, the correlation function. But the sample autocorrelations, whatever we have got, these are the sample autocorrelations that we have got for different lags. And what we say is, this is what is called as a correlogram. Whatever the different sample autocorrelations that we have got for the data for different time lags, we call it as a sample correlogram. And now, if I try finding out the distribution of the sample autocorrelogram, okay, let me try to find out the average of this sample autocorrelogram. It's very close to 0. And let me try finding out the variance of the sample autocorrelogram. Let me try finding out the variance of this. This is around 0.001. Now what it says is, the distribution of the sample autocorrelogram, if it is normal with a mean 0 and a variance almost equal to 1 by t. Let me see what is 1 by t here. T is 16, right? So this is 0.06, or here my sample size is 485, right? I should find that the variance of this sample autocorrelogram should be somewhere around 0.002. I got it as 0.0017. So more or less, the variance is more or less similar to that. So that is when I call it as a white noise. So if I try finding out the sample autocorrelations or correlogram for a data, and I find that the mean is coming very close to 0 and the variance is coming very close to 1 by t, which can help me in doing the 95% prediction interval quite comfortably, which means all my sample correlograms should be, if I look at the 95% confidence interval, it should be 2 multiplied by 1 by square root of 485. So they should be in the range of plus or minus 0.09. So anything in the range of plus or minus 0.09, that is what we are seeing. Majority of the autocorrelations are there in the range of plus or minus 0.09 itself, which is what is a very clear indicator that this is as good as a white noise only. Similarly, I could look out for I could look out for partial autocorrelations, which we have already looked at. Again, in case of partial autocorrelations also, none of them are beyond that plus or minus 0.09 level. So, which is a very clear indicator that this could be as good as this is as good as a white noise itself. And a few more important dimensions to look at in this context is look at the correlation squareds and multiply it with the sample size and the sum them up. Right. So if I look at these are the autocorrelations. So what I'll do is I'll do the autocorrelation squared. I'll do the autocorrelation squared is okay. This is the autocorrelation squared and I multiply it with the sample size. Right, so this becomes the autocorrelation squared and I multiply it with the sample size. Now what we say is autocorrelation squared multiplied with the sample size, it should be similar to the chi-square distribution with degrees of freedom equal to 1. So let me see the chi-square distribution. Chi-square distribution with the degrees of freedom equal to 1. So you see the probabilities of a chi-square distribution with degrees of freedom equal to 1. Chi-square distribution with degrees of freedom equal to 1. Okay, so you see you don't find the extremes here. 0.94, which is so if I take 1 minus of it, so this is 0.96, except for this, which is crossing the 0.95 mark, all others are significant. So which is again an indicator for me that this is following a chi-square distribution with the degrees of freedom equal to 1. And one more important test I can do is some of the independent chi-squared variables. So if I am taking the summation of the independent chi-squared variables, let me take these are all independent chi-squared values. So I'll take the summation of the independent chi-squared variables. This is the summation. What we say is it should also be chi-squared with degrees of freedom equal to the summation of the individual degrees of freedom. Now individual degrees of freedom is 16. So I'll try to find out the probability that is associated with this particular value. It is I'll try to find out the chi-square that is associated with this particular value with a 16 degrees of freedom. This is also is around 0.33, which is lying within that range itself, because if I look at the 95% confidence interval, this is very much applicable. So this, even for a large samples, I can use this Box-Pierce Q statistics to look out whether my value is following a chi-square distribution or not. Similarly, I can use a junk box Q statistic also. The only difference being I'll replace it with t plus 2 instead of directly taking a simple summation. I will go with, instead of doing a simple summation of the chi-square of the correlation squares, I'll take the correlation squared. I'll take the correlation squared and divide it by t minus 2 divided by the 1 minus lag. So basically if I am doing it like this, I'll take the correlation squared. This is the autocorrelation that I have got, and I divide it by t minus 2. T is 485. 485 minus 2 is 1 here, 2 is 2 here. So better I create the lag as one variable just to understand that concept. I'll take it as 1, 2 here. So here I would be creating the autocorrelation squared, and I divide it by 485 minus 2. So I'm doing a small weightage here. So this is what I'm doing it as a weightage, and this total is what I'm adding up, right? So if I want the Q for a junk box statistic, I am simply adding up not the direct correlation squares, but I am doing a weightage on the correlation squared. I am adding it and I am multiplying it with t and also t plus 2. So this is giving me that this is 13.31. The same I am trying to apply. This is more and more applicable if the sample size is much smaller, and even in this case I am trying to find out the probability with respect to the chi-square distribution, looking at it with 16 degrees of freedom. Again, the degrees of freedom and all remain the same, and when I'm trying to do it, even this is within the 95% limit itself. So what we could clearly see is, if at all I want to get into understanding the cyclicality, the white noise that is present in the data, or is there some amount of serial correlation that is present in the data, I need to understand all these concepts to a very detailed extent. Now what we can very well look at is, now that we know the basic concepts of cyclicality and the important definitions that are involved in the cyclicality process, the basic structure of the cyclicality process. Now we are in a position where we can get into the understanding of the very important time series models, which are called as moving average processes, autoregressive processes, autoregressive moving average kind of processes as well, right?